So, let us get started with the basics of L1 regularization and some algorithms towards that. So, we have seen earlier when we discussed regularization ideas that we need to set up a cost functional subject to regularization constraints. And we saw the theory behind Tikhonov regularization, where we need regularity constraints to make an ill-posed problem into a well-posed problem. Okay. So, what sort of constraints do we want, or what constraints do we need to set up? So, that depends upon the geometry of the problem. For example, if I look at the cost in terms of the square sum of the squares of the weights, then that is more like taking the induced norm and I want to minimize that norm somehow in the L2 sense. But that may not be the constraint I may be interested in. I may be interested in figuring out how many non-zero elements are there in my weight vector, and I want to minimize the number of such non-zero elements, right. Not get into a trivial thing, but at the same time I want to minimize this number within some norm, within some distance, and here I can bring in the L1 norm, right. So, therefore, greatly the regularity constraints we impose on the problem really depends upon the geometry of the problem at hand and the practical constraints that will drive us towards these algorithms. Okay. So, let us get formally started with these basics, and I will motivate L1 regularization, the need for L1 regularization, the need for L1 regularization. I will also talk about how the unconstrained and the constrained optimization framework can be set up, and we will look into some algorithms towards this problem. Okay. Now, first and foremost, we would like to know what issues we may face with L2 regularization, right. Issues we may face with L2 regularization. So, let us consider the case, where we have two variables in a weight vector. Okay. We have a weight vector, we have many variables, we consider two variables and let them be W1 and W2, right. And what we want here is a scenario where W1 and W2 are highly correlated, right. So, if W1 becomes larger, then W2 becomes much smaller, in a way cancelling the effect of W1, right. I have two variables W1 and W2 within this weight vector that are highly correlated, and let us imagine that W1 increases and W2 decreases in a way which cancels the effect of W1. This leads to models that can have high variance. That is, it can work under certain conditions, and in the predictions can be subsequently quite different, right. The models can have high variance, which means we can have different predictions under the residual square sum metric, RSS metric, which is residual square sum. Now L2, the geometry of L2 is within this ball, right. So we want to optimize something on a circle, or if we put regularity constraints in L2 such that it is lying inside the circle or outside the circle, that is the geometry of the problem in L2, right. The issue that we are facing here is we do not look into account, we do not take into account the sparsity of the model, which means we can have variables that may not be linked to the problem, or in the case where they are highly correlated, we may have a situation like this where one cancels the effect of the other. So can we bring in a different kind of geometric field to the problem that that motivates L1, right. So let us consider further here. We considered the regression problem earlier, and given my data matrix X, which is my n by k matrix where each vector xi belongs to Rk, and y is my n by 1 data response vector. So basically I want to get the best fit of a line to this data subject to some regularity constraints, and we saw that solution to that line was of this form. And that corresponded to the minimum norm solution, right. So we have seen this this problem. Now the way you set up the cost functional is as follows. You have x w minus y, and you want to minimize this norm, the L2 norm, the square of the L2 norm, subject to the norm on the weight, right, and w must not be too large. So in that sense you would like to balance the large variables, or what I mean is those coordinates of the weight vector that are significant in a way that meets the target cost, right. We have a certain cost and we want to optimize that cost. So, some variables should not blow up. So, in that sense we want to adjust the selection of our weights in this setup, right. And this can give us issues that I discussed earlier, that if you have correlated variables, I mentioned to you that if one grows large other becomes small in a way that cancels this effect. So, therefore, you can have different predictions under different conditions, but the calculus is sort of smooth because you can kind of work through the math under the L2 norm constraints, because it is a quadratic cost, it is a convex optimization problem. So, therefore, you know you are sort of within that sandwich bound. So, you can get towards the unique solution that you want, optimizing this quadratic cost. But let us pause for a minute and ask the question, under practical constraints, for example, when we deal with neural networks such as the backpropagation algorithm, etc. If we have dead neurons or synaptic weights that are insignificant, do we want to retain those weights? And this problem is practical because of two reasons. One, computational complexity and memory, right. If you have to save all those weights for doing your computation, it requires memory. Two, if it is insignificant, it is a burden if you want to put within the computation engine, right. So, it is these models that come from L2 are not parsimonious, right, they are not stingy. So, let us see this in terms of what the setup of the problem is, right. L2 norm, just to recap what I just told, I am going to write this up. L2 norm, one does not account for the parsimony of the model, that is, we do not account for the sparsity. And a related consequence is L2 models may have non-zero values associated with inconsequential variables. That means those variables which are not useful for us. A related example to this idea of inconsequential variables is, for example, I have a DNA strand and I am looking at these nucleotides, and I can think of maybe 100 features that I want from this data. But from this I want to make some inferences into gene expression that is possibly my outcome. I may not need 100 variables, possibly I may need 40 or 50, right. So, there are a lot of inconsequential variables which I need to weed them out. And how do I decide this set? This is where the question comes as to how to choose the variables that I want and what to weed out, and that is very model specific, that is very problem specific. Okay. Now let us delve into the case where we want to impose L1 regularity constraints on the weight vector. Okay. Now cause involving L1 penalty impose sparsity constraints. Right. So L1 is typically like this. You take the absolute value, you sum the absolute value on all the coordinates, and that's what it is, and you want that sum to be less than some number, pre-imposed number that you want. So in that sense, if the data matrix X has irrelevant features, right. So if the data matrix capital X, which is the n by k matrix, I have n data points and dimension of each data point is k. So if this data matrix has irrelevant features, L1 seems to be better than L2, so which implies that we have a low variance feature selection. Second, L1 can yield a better variable / attribute selection because it throws away the irrelevant features. And what is the consequence of this better variable or attribute selection? So there are three consequences. One, it leads to simplification of models for interpretability. This is very important because we should be in a position to interpret the data and make sound observations from the models. So if the model is simplified, it is good for us. From the learning perspective itself, this can lead to shorter training times. And last but not the least, we avoid the problem of overfitting, and this also implies we avoid the curse of dimensionality. Right. So this is sort of a motivation why we might want to use L1 regularization as opposed to L2. Now let us set up the unconstrained formulation. So minimize, I consider the same regression problem. I look at this L2 norm between x times w minus the response vector y. I want to minimize this norm, square of the norm over all choices of w, subject to this constraint. So we are bringing in the L1 norm. So I just call this equation 1, right. A small twist than what I did with L2. In L2, when we looked at the L2 norm here, we want to minimize this x w minus y subject to the minimum norm of the weight vector w. So there I could bring in the L2 norm would be just summation I equals 1 to k w I square, right, where you have coordinates w1, w2, so on till wk for your weight vector. And that was the geometry of that problem. And doing the math, you could exactly get a closed form expression for that cost. Now L1 is slightly different, except that in the regularity constraints we bring in the L1 norm, that is we bring in sparsity on the variables in the weight vector. So the sign becomes very critical when you bring in the sparsity constraints, because you have w1 plus w2, w1 minus w2, all possibilities you have, and over those constraints, over that bounded box, you have to solve for your quadratic cost. Okay, that is the feel of the geometry of this problem. Now what is the issue with this setup, right? Clearly equation 1 has issues of differentiability at the origin when w is some coordinates of w, because this norm is mod w1 plus mod w2 plus dot dot mod wk, and when I have to take the derivative of this with respect to the individual coordinates, I have a problem, because mod x is not differentiable at 0, right. This is from our basic calculus. So therefore closed form solution is hard, directly you cannot get the solution the way you did for the L2 constraint. Now let us look into the constraint formulation. The only difference between the unconstrained and the constraint formulation is the norm on w. I want to I want to bound it within a certain bound, right. I can say the norm of w is less than or equal to t or something like that, right. I want to bound that norm. Subtle difference, but this will have consequences when we have to set up our optimization problem. Okay. So let us consider the problem here. I want to minimize over all weights this Euclidean norm x w minus y, that is L2 norm squared, subject to the constraint that the L1 norm of w is less than or equal to t, where t is some chosen value. So in this case I will look at the absolute value of the weights, and I want to look at all those non-zero variables in my weight vector, and that sum has to be less than or equal to t. That is the meaning of the statement, right. The sum has to be less than or equal to t. Okay. Now what can happen here is non-differentiable, I call this equation 2 before I begin, okay, non-differentiable constraints are converted to a set of linear constraints, and this implies that the feasible region is a polyhedron. And when we deal with some homework exercise problems, you will see the picture of this this optimization with these constraints, right. So I would also advise you to look through the lecture on norms in one of my video lectures in the course Mathematical Methods and Techniques for Signal Processing, where I discuss the geometry of all these normed spaces. So this is for your understanding, okay. So I do not want to discuss all that again here, because you have videos there that will pinpoint to these details, okay. Now given this regularization problem or the L1 regularity constraints, we would like to now discuss algorithms that can solve these optimization problems, right. We would like to discuss algorithms for solving these optimization problems, and one of the popular algorithms is the lasso. This broad heading I would say is algorithms. Now the lasso stands for least absolute selection and shrinkage operator. It is a very popular technique in statistics, and this evolved from Tibshirani. We will discuss this procedure, but before we discuss this procedure, let us motivate this by considering the solution to the constraint optimization problem, which is given by equation 2. Suppose we have two variables in our vector W. Let us say this is W1 and W2. What we do is, by considering the sign of W1 and W2, we have four possibilities. We have W1 plus W2 is less than or equal to t. I can have W1 minus W2 is less than or equal to t, minus W1 plus W2 is less than or equal to t, and minus W1 minus W2 is less than or equal to t. And this is sort of my set of constraints. So you can plot this in the W1 W2 plane, it is straightforward set of inequalities. I have 4 inequalities. You can plot the graph, right. You have slope of 1, slope of -1. You can imagine how this geometry looks like, right. So, I will leave this as a homework, because as a graduate student you should be able to do this. Plot the constraints on W1 W2 plane and show the feasible region. So, what it means is our solution should reside in this feasible region, and what we are trying to solve is the original cost, which is the L2 constraint that we have, right. We solve for the L2 constraint subject to this set of linear constraints that arises because of the L1 regularity constraints we impose on the problem. Okay. So, now going further, any minimizer to the residual square sum subject to these constraints that I indicated here, right. So, I look at the residual square sum, which is the L2 norm of x w minus y, the L2 norm squared, and any minimizer to this subject to this these constraints will minimize our cost. And the cost is given by equation 2, which is our optimality, which is our constraint cost formulation. Now, do you see a problem here? If I have k variables, I can have 2 power k linear constraints, right. So, if we have k variables, we have 2 power k constraints, and this implies it is an exponential increase in complexity. I mean, to just get a feel for this problem, suppose I look at vectors in a 40 dimensional space. This is the number of constraints I have, right, over R40. I have 2 power 40 constraints, and this is infeasible for optimization, right. These days you have high amount of computational machinery, cloud computing or computing with multi-core processors, etc., and you can set up this problem and you can launch them, but even then it is computationally expensive, and if the number of variables scales, like from 40 it goes to 100, then you are really infeasible towards a solution. Okay. But let us see what you would do to solve this problem. I mean I will mention Tibshirani's approach. So, we start with the constraint set which is null, and you go through this loop while norm L1 norm of this weight vector is less than or equal to t. What you do is you add the sign of your weight vector w and fold this into the constraint set. And then you optimize this norm of x w minus y subject to the constraints. So, these are the two things that you have to do in the while loop, and you come out of this while loop as all the constraints, after all the constraints are satisfied, right. After all the constraints are satisfied, you come out of this while loop. So, in practice t can be small, but still this is an exponential cost in the way you would have to solve this problem, but using this approach you can solve the problem. So, you start with a null set, then you go through this while loop. As long as the L1 norm is less than or equal to t, you add sign of w and fold this into the constraint set. So, I look at first case as w1 plus w2, or and next I keep adjusting these and I optimize on this L2 cost subject to the constraints, and every time I look at all the possible constraints by the sign changes, and then I have to solve for my L2 optimization. So, every time there is initial condition which changes because I am adding new constraints. So, whatever I solved earlier may not be a good initial condition for the next, and that leads into interesting algorithms towards solution of this problem, right. And from this we can loop through this, and at the end of completion of this loop we can arrive at some w which satisfies all these constraints, and that is our solution to this problem. Okay. So, there are some practical considerations, and that we will discuss shortly.